do a quick, maybe 15, 20-minute thing. So,
Okay, we are rolling.
okay.
Good for you.
Hello, everyone. Welcome back to another Learning Glass session. Today, we'll talk about combustion using the first law analysis to get an idea of the final state of the products. And of course, the important thing about the final state is the temperature. So by using the first law of thermodynamics, we can balance out this energy between the chemical bonds, heating up, cooling of reactants and products, and any heat transfer that can occur out of the system to the surroundings. So that gives you, that balance will give you the flame temperature, which is basically the temperature of the product stream outside of the system. So say you were to have this combustor, blocks, flow reactor, where these reactants came in, let's call them R reactants, at 100, it just said 100 Kelvin. They're cold reactants, some cryogenic rocket fuel that's kept cold, and the products come out at 1500 Kelvin after there's combustion reaction. And what would happen is that in between there's some process and there's some heat out, or just some amount of, it's not a rate, some amount of heat that gets out of the system. So given these temperatures and the fact that the enthalpy of combustion, which is the enthalpy of the reaction, is this negative amount, because the enthalpy of reaction is the bond energy of the products minus a bond energy of the reactants. So because this is exothermic, it's a negative value. The products are higher. The starting point is higher. So this is a typical range of hydrocarbons, but also assume that Cp of the reactants is a constant value at 30 kilojoules per Kelvin. This is a big Cp, constant. And this is also a typical value. So these are typical values you would see. It's not typical to have a constant heat capacity because this is an inaccurate estimation, but it can give you a ballpark answer. So if you apply some reasonable value, you would get reasonable numbers. So the product's heat capacity assumed is a constant value at 60 Kelvin. So what happens in terms of the heat capacity, it has a T to the 1/2 dependence. So if this was temperature and this was the Cp, heat capacity, you would see a behavior like this. So what these values represent is some constant value to change from 100 Kelvin, 100 Kelvin to 300 Kelvin. And then at the final temperature, this is the standard state. So what we're doing is we're choosing some average values. So this would be an average value. This would be the average value. So assume average constant values. That's what we're doing here. So this would be this average of this process. So that the products are going to go from the standard state to 1500 Kelvin, applying this value here, something representing there. So that is an assumption you can make, and if you give reasonable numbers, you'll get something in the ballpark. The most accurate would be to say that if you were to try to find this enthalpy change of the thermal process, that would be, H products minus H reactants from a table. That would be the most accurate because tabulated values are pretty well established for these hydrocarbons, and you can get a pretty accurate number if you do the right analysis with the right tables and account for all the mass and things like that. Or if you had a model for the specific heat as a function of temperature, you can account for this temperature function, integrate it over this temperature change, and that would give you a pretty good result. Or, like we do here, you can estimate some constant value, some average, to say Cp delta T. So that's what we're doing here. Okay, so given this situation, how do we use the first law? Well, starting from the beginning, we would say this process doesn't have any work. Combustors, we analyze those by separating the work part from the reaction part. In many cases, we want to use this high enthalpy product to get mechanical work. So what we do is we take this product and we feed it into the next process and do an analysis on another separate analysis. This is just isolating this combustor process, which is just on the chemical bond change and the thermal enthalpy changes and heat transfer. So the heat transfer part, it's going to be Q out, of course. So of course, this, the energy transfer in between is balanced by the change of state from the final to the initial. So that's a final is the products, initial is the reactants. Okay, so if we say that this is this total absolute value of heat transfer over all of the moles reacted, of course, that's what this little q means. So that would allow us to say that big Q equals and all of the products so this is the absolute heat transfer. We know it's going to be heat transfer out, but let's keep it in this other notation where positive Q is Q in, negative Q is Q out, and so forth. But this is just Q at the other notation. So that is the same thing as saying, okay, then we're going to write this enthalpy for the products and the enthalpy of the reactants. We're going to separate out their chemical bond components and their thermal sensible enthalpy change components. So this should be sensible thermal. That's only related to CPT. This, if you have a chemical reaction, you have to add in the chemical part in here as well, which is this formation enthalpy. But if you're talking about this sensible heat or the thermal change in enthalpy, it's related to CP. Okay, so if we expand this into the chemical and thermal part, we would write the enthalpy like this. All of the products times their chemical bond component, which is, we express this in terms of the formation enthalpies, then some enthalpy change from some reference. So this is the thermal part I was talking about. This is the chemical bond part. And then the reactant component. So this is products, this is reactants. Okay. So, okay, we can rearrange this. Let's bring all the chemical bond parts together and all of the thermal parts together. We could say that this equals so that's the chemical bond part. This is the thermal energy change. So this is a product temperature, the reactant temperature. Okay. So this thermal part, we're going to assume using a constant heat capacity. If you assume some average value, it's related to Cp delta T, and we're getting there. So this is the enthalpy change due to chemical reaction. That's what this enthalpy of combustion is. So another way of writing that would be in terms of Hess's law, in terms of these formation enthalpies, and so forth. So this actually should be N. So N fuel, that's what's given. It's not per kilogram. We know the amount of fuel. So we multiply that by the enthalpy of combustion to get this absolute value. It's not per gram, it's not per mole, it's kilojoules. So we're getting there. CQ equals combustion Okay. So then we can apply this assumption in here. That will give us applying this assumption, the heat capacity of the products times the temperature change of the products difference from the to the standard state, from the standard state to the product final temperature. So we have everything there. We can plug in the known average heat capacity, some average for the reactants, the temperature change that we know goes from 100 to the standard state, the what I meant here, that this was 400, sorry about that. This is actually 400, so the difference is 100 Kelvin here. And this is 1800, so the difference if the standard is 300 Kelvin, so let me plug in those final. So the number I got was given that the difference from this to the standard state was 100. The difference from the standard state was 1500. So applying that, you would say Q equals negative 100,000 kilojoules plus 60 kilojoules per Kelvin times 1800 minus 300. That's the standard temperature, approximately, minus 30 kilojoules per Kelvin times 400 minus 100 Kelvin. So that's where I got the 1500, that's where I got the 100. This should be 100. So balancing that all out, what I got, Q out, and then, okay, so another thing, so if you do this math, you should get that Q, this algebra, arithmetic, is negative 13,000 kilojoules, which equals Q in minus Q out, because that's the definition of this symbol here, is the net heat in, so that means Q out equals 1300. There's no Q in, this is exothermic because the enthalpy of the reaction is negative, and from our experience we should know what direction heat goes in. So that's the final result there, where given the temperature difference or the temperatures, we're always evaluating the chemical bond energy at the standard reference state. That's what we can find in the tables. So with that, that's all we had today. So thank you. We'll see you next time.
Do you want to stop?
Yes, please.